Hi, I'm Alyssa, and together with my co-author Hani, we're going to be giving you a talk about our paper, CrossTalk, Speculative Data Leaks Across Cores Are Real. So today we're going to talk about interesting ways we found for reverse engineering CPU pipeline behavior, the tool we built to help us use these ways, and also the awesome results that we found. But first, story time. So in this story, we have a witch and we have Bob. Or rather, we have the code that Witch is running and the code that Bob is running. And Bob's code is protecting some kind of confidential information, such as private user data, passwords, private keys, and the Witch really wants to access this data. But thankfully, these are isolated, maybe separate processes, maybe in separate virtual machines, but still on the same CPU. And it turns out the Witch can use a bunch of spells or transient execution vulnerabilities that take advantage of issues in the way CPU pipelines are implemented and still lets the witch jump over this isolation boundary and access Bob's secret data. We can simply solve this by just running the witch's code and Bob's code on separate CPU cores, which means that even if there are bugs in these CPU cores, Bob's data should still be safe. Since all of these security issues are now solved thanks to this isolation, we can use these vulnerabilities for what they're really useful for, CPU reverse engineering. It turns out that in particular, the MDS vulnerabilities in Intel CPUs mean that we can observe the contents of some of the internal CPU pipeline buffers. And if we just run code and then just watch what's in these buffers, we get a good understanding of what's going on. This can just be expected memory reads and writes, but it can also be unexpected memory accesses, such as the CPU walking over page table entries, or even more mysterious things. To work out what's going on, we needed to look a step further.
Hi everyone, my name is Hani, and I am a PhD student at FUSEC. So, since the main requirement of all transit execution attacks is the co-location of attackers and victims on the same core, the solution to all these attacks seemed to be the physical isolation, where attackers and victims run on separate physical cores to avoid sharing any core private resources that might contain observable sensitive information. So we started looking at different performance counters to study the behavior of x86 instructions, but beyond the CPU core boundaries. And we found counters which are monitoring the off-core requests and responses during the execution of an instruction. Some of these off-core requests are actually quite intuitive. For instance, when we execute the seal flush instruction, it needs to go off-core to flush also the last level cache. And when you execute the CPID instruction, it can go off-core to recover the branch string of the current processor from the power control unit. Last, when we execute the RDRAND instruction, it needs to go off-core to obtain a random number from the digital random number generator. As you can see, all these are system-wide resources and are located outside of the CPU core. Resources such as the digital random number generator are shared between all cores, and we discovered an off-core staging buffer, which is shared between all CPU cores and is used to temporarily store the data returned from these off-core resources. And therefore, all off-core responses directed to any core are actually visible to all CPU cores in the system. So to analyze these off-core requests and responses, we built CrossTalk, a profiler for analyzing complex microcoded instructions which perform off-core requests. And by leveraging transit execution attacks like MDS, CrossTalk analyzes a shared staging buffer located outside of the CPU cores, leaking across cores the content of the off-core responses directed to other physical cores in the system. CrossTalk consists of two main components. The first one is the instruction generation stage, where we prepare the correct profiling environment for all x86 instructions. The second one is the instruction profiling stage, where we first check whether an instruction makes an off-core request or not. And in case it does, we analyze then its stage and buffer interaction during its execution. The last step is where we keep the relevant instructions, which can be used as cross-core leak primitives in the exploitation stage. For now, we're going to focus on the staging buffer analysis part. So let's assume that we have one physical core with two hyperthreads. On the first one, we execute in a tight loop the CPID instruction, requesting over and over the branch string from the power control unit. The microcode of CPID will initiate an off-core request to the power control unit, which will write the branch string to a specific offset in the staging buffer. Later, the microcode of CPID will copy the entire staging buffer to the local line fill buffer of core 1, and then will return the offsets containing the branch string to the program. Now, we execute on core 2 a target instruction which makes off-core requests that we would like to profile. In this case, we're executing RDRAND. The microcode of RDRAND will initiate an off-core request to the digital random number generator located outside of the CPU cores and ask for a random number, which the DRNG will write to a specific offset in the staging buffer. Later, the microcode of RDRAND will copy the entire staging buffer to the local line fill buffer of core 2, and then the offsets containing the random number will be returned to the program. As we can see, now we have an identical copy of the staging buffer in the two local line fill buffers of core 1 and core 2, both containing the two off-core responses requested by each other, but each core is interested only in specific buffer offsets defined by its corresponding instruction. Now, if we run the riddle attack on the second hyperthread of core 1, we can leak the content of the local line fill buffer containing also the random number returned to core 2. So during our reverse engineering, we observed different properties of the staging buffer. First, different instructions write to different offsets within the buffer. Second, instruction operands determine the offsets where the off-core responses are written to. Third, different instructions might write to overlapping offsets within the buffer. So with these properties, we still have one major challenge to be able to leak the victim's off-core response, which is how can we distinguish between the victim's off-core response and the noise within the leaked staging buffer. We were able to leak the victim's off-core response in 3 steps. Step 1, we bring the staging buffer to a known state by executing a series of instructions which can cover the entire buffer with known data. Step 2, we execute on a different core the target instruction we want to profile, which off-core response will overwrite some offsets of the staging buffer. Step 3, we compare the current staging buffer with the one in the first step to find out the offset that have been overwritten and the content of the off-core response returned to the target instruction. Here is a list of some instructions we profiled with the corresponding staging buffer offsets and the off-core responses that we observed. Now, I will hand it over to Alyssa, who will tell you more about how we exploited this vulnerability and how it got mitigated.
As a concrete example of such an attack, consider an SGX enclave calculating an ECDSA signature. For example, an SGX attestation. In such a case, the attacker obtains a signature, R, S, so both R and S are part of the signature, and they do not have the private key which is safely inside the enclave. Of course, an attacker wants the private key, so we can look at how the signature is calculated with this equation and rewrite it in terms of the private key. Remember, the attacker has the message signature, so the R and the S, and they know what was signed. What that means is the only thing left is the randomness, K. Again, the attacker has the signature and the hash, but they do not have the randomness, and so typically they cannot recover the private key. Of course, the only source of randomness available to this enclave is RDRAND, and that means that when it needs such a key, it will generate it using RDRAND. And typically, for example, Intel's SGX libraries, they will simply take RDRAND and use that directly as K. That means that thanks to CrossTalk, we can simply read the randomness from the buffer as it's being generated by the enclave as it does the signature, and that gives us the contents of K. And that means we can simply fill it into the equation and recover the private key. It really is this simple. You can obtain a private key from such an enclave with only one signature. So now we're going to do a quick demo. On one core, we're going to preserve both hyperthreads. We're going to run a sniffer which just basically uses the primitives we found to dump the contents of the staging buffer. On another core, we're just going to call rdrand in a loop. We're going to do it slowly because we want you to be able to see what's going on. You can see the contents of the staging buffer are changing every time we call rdrand. And for example, you look here, so rdrand was A8, F8, and you see this again in the staging buffer dump. If we pick the previous output of rdrand, then again, we also see this output from the staging buffer. We're now going to try the attack on the SGX enclave, and done. We only need the one random number, remember? And so we simply go there, we use SGX step to single step, we leak rdrand values, and we just join them together, and we recover the key. This, of course, led to a whole bunch of drama, as is typical with these fancy microarchitectural papers. We got a CVE and a fancy name from Intel, and we got an extremely long embargo period. We also got some very impressive looking performance loss numbers from the mitigation. So what's going on with the mitigation? So Intel released a microcode update, and they made some instructions way slower. In particular, the random number instructions and one of the SGX instructions that was also affected. The new microcode locks the entire memory bus for the period of the instruction while it obtains the result from the staging buffer and clears it, which prevents other cores from accessing this data in the meantime. What's interesting is we can go back and use the CrossTalk tooling to actually check, does this make sense? Is the described mitigation actually probably what's happening? So we look at the performance counters before and after the microcode update, and we see that the number of cycles has indeed drastically increased as we'd expect. And interestingly, the number of micro-ops has massively increased, and that probably means that it's busy looping, waiting for the response and for the buffer to be cleared. And since clearing the buffer means more off-call requests, we'd expect more off-call requests, and indeed, we also see this. Of course, this is only relevant when you're actually running these instructions, and of course, you do not run these instructions in a loop, you just run them enough to get some entropy for your random numbers. There are obviously an awful lot of things we didn't mention here, such as more results from our tool, in particular, more performance counters, details of what you need to exploit and how you do it, a covert channel just for fun, the affected CPUs, and more. Please, hopefully the paper is super readable. Feel free to ask questions. You can also find more information on our website, or you can bother us on Twitter. Thanks for listening.